Hello. Okay, so we are back to Markov chain Monte Carlo. So let me real quick try to review the part that we did in the previous lecture. So we are trying to generate samples from a given distribution. And for simplicity here, I'm taking the distribution to be discrete. And so the target distribution is mu I is the probability that x, random variable x, is equal to I. So we want to generate samples basically based or derived from that distribution. Okay, so we have an iterative algorithm that basically is related to Markov chains, as we will see. So suppose that in the nth iteration, xn is equal to I. Okay, so I is one of the possible values of the discrete random variable we are interested in. So xn is equal to I, and so the question is, this is generation of random variables. The question is, how can we generate the next sample? So basically, you can think of it as a two-step process. The first one is like you have a candidate for the next iteration. So the candidate is chosen based on a given distribution, a proposal distribution. Okay, so for each state, like I here, you have, with probability Qij, you will propose J as the next state, as the next value for the discrete random variable. But this does not mean that x of n plus 1 is equal to j. Okay, so what you do is that x of n plus 1 is indeed equal to j, but this happens probabilistically. So x of n plus 1 is equal to j with a certain probability that's called the acceptance probability. And this probability, it involves basically computing this mysterious quantity. Okay, so if you see here, basically it is mu j qji. Qji is basically the probability of proposing I as the next state if in the current iteration, basically x of n is j. Okay, so so have mu j qji over mu I qij, and again, because there is no basically restriction that this ratio, it may be greater than 1, and so we will basically have minimum of 1 and this quantity. If it's less than 1, then that's the acceptance probability. If it's greater than 1, then the acceptance probability is 1. And now with 1 minus the acceptance probability, x of n plus 1 is the same state, which is I. Okay, and so so the algorithm basically proceeds using this idea here, and you need to provide it with, of course, the target distribution. So the target distribution, because you need to have those mu's, and also you need to have those proposal distributions. Okay. Basically, my claim at the last part in the previous lecture is that we have a discrete time Markov chain with a specific transition probability matrix. Okay, so first, if you look here, suppose that x of n is equal to I. I mean, so what was the best? What was x of n minus 1? What was x of n minus 2? They were whatever they were. The idea is that by construction, the future x of n plus 1 is conditionally independent of the best, given x of n, that x of n is equal to I. Everything here to derive x of n plus 1, you have no business with the previous outputs of the algorithm. Okay, so we have the Markov property built in. Basically, given that x of n is equal to I, you use the Qij's to choose a candidate as x of n x of n plus 1, and then you accept it with some probability, or you keep the output at y with 1 minus that probability. Okay, so it's a Markov chain. What is the TPM? So the probability of making a transition from I to j, so that's Pij, is it's the multiplication of two basically factors here. One of them, so to go from I to j, you need first to propose j, and this happens with probability Qij. and then if you propose J again, you can accept it or not, and so you need to multiply by the probability of acceptance. Okay, so this is the transition probability from I to J. And you can basically, because of this minimum here, you can divide into three states, three cases. Perhaps this ratio here is greater than 1, and if it's greater than 1, or actually if it's equal to 1, in both cases, the first and second cases, this minimum will be 1, and the transition probability from I to J will be Qij. Only when this fraction here is less than 1, then the transition probability from I to J will be Qij multiplied by this, and so Qij will go with Qij, and you are left with mu J Qji over mu I. Okay, and so those are basically the transition probabilities, and they depend on those quantities that you provide to the algorithm, because you will provide those mu's. Again, the mu I or mu k is the probability that the random variable is equal to k, and again there is a target distribution that you want to generate samples from, and then things also will depend on the proposal distributions. Again, something that you feed to the algorithm, and let's just assume that you will do so in some nice way. Okay, that is not problematic. Now, let's take this Bij and multiply it by mu I. So if you multiply it by mu I, again, it's just to multiply. So each one of those terms here will be multiplied by mu I, and this last term here will be mu J Qji. Okay, so just keep this. Now, Bij, Ing, and generic values of the random variable, generic states. Okay, so what about Bgi? So Bgi is basically, it's the same formula, but you simply, swap the roles of I and J. So now you need Qgi, which is, the probability that given, that in the current iteration, x of n is basically is J. Then basically you propose I, basically with probability Qji. And then it's accepted with a certain acceptance probability. Again, it's written just by swapping I and J. Same thing. You can write the minimum. You can divide into three cases, and then you say, okay, what if I multiply by mu J? So if you multiply by mu J, then you get basically those quantities. Just each line here is multiplied by mu J. Now, here is an interesting thing. If you compare these two guys, mu I Pij and mu J Bgi, which is, if this is true, if mu J Qgi is greater than mu I Qij, if this is true, then actually these two quantities are the same. And if this is true, then the two quantities again are the same. Now, the middle line, here you have mu I Qij, and here you have mu J Qgi, but basically we are here, this case is the case in which mu I Qij is equal to mu J Qji. So basically we have equality, and this is for any generic I and J, and so we are talking about a very specific Markov chain. It's a Markov chain such that for every I and J, for every two states I and J, we have this is satisfied. Mu I Pij is equal to mu J Pgi, and this is by design. Okay, and so if you wonder, basically why having this quantity here, well, it's designed such that you get this. You get this basically equality here, this identity that for every I and J, mu I Pij is equal to mu J Pgi. Okay, so we have a Markov chain, and again, you need to take some precautions. We don't have time to study them or talk about them. But let's suppose that actually our Markov chain has a stationary or invariant distribution, and let's try basically to take the mu's. Remember, the mu's are not, it's basically those are the target, the target probabilities. PMF. So what will happen if you take this vector of mu's and multiply it by the transition probability matrix, which is basically, it has elements that look like this or that. Okay, so you have, let's do the multiplication. Let's basically multiply this row vector by the jth column in matrix P. So if you do this multiplication, you will get summation over I, mu I, and then Pij. So this is, again, you take the vector and you do the multiplication column by column. And so this is what you get when you multiply this row vector by the jth column in the transition probability matrix. Okay, so this is something that is you do always. But now there is something particular about our Markov chain here, which is that it satisfies this equality for every I and j. So now you wrote down this, this summation, but what you can do is that you can replace mu I Pij with mu j Bji. Again, as we verified that this is true, these two quantities are by design, they are exactly the same. Now, we are doing a summation over I. This was the original objective, is to multiply this row by the jth column in the transition probability matrix. Now we rewrote this quantity in terms of mu j. Mu j now is, j. It's while the summation index is I, so I can take it outside. And then we are left with a summation over I of Bji. So what is this thing? This thing here is that you fix a row j, and then you sweep through the columns. And so that's the sum of the elements on the jth row in the transition probability matrix. And so that's 1. 1 multiplied by mu j, so it's mu j. So this means that this product here is equal to mu 0, mu 1, mu 2, and so on. So in fact, the target PMF is, if you design your algorithm to run as such with those acceptance probabilities, what you will get is a Markov chain whose stationary or invariant distribution is the target PMF. It's the PMF according to which you want to generate the samples. Markov chains, that satisfy this identity here, they are called time reversible chains, and then they appear a lot. And as you can see, that you can easily verify that once this identity is satisfied, then once you have this property, then you have this stationary distribution. Okay, and so and there are basically analogs to this in continuous time Markov chains. So also you can talk about time reversibility in continuous time Markov chains. Okay, and then there is something nice about this algorithm, which is that in many cases, in many practical cases, especially in big data and so on, sometimes we have a PMF. Okay, sometimes we have those guys here, but it is unnormalized. Okay, so suppose that that your probabilities are some constant, some constant C multiplied by numbers, and like you don't know C, or it will be like very difficult to compute C. The algorithm does not really require this. It can work with unnormalized distributions. And the reason is, again, by design, is that the quantity here in which mu appears, it basically is a function of a ratio. So here is mu j and here is mu I. Okay, so basically, if you know that mu I is equal to some constant C, mu I bar or something like this. Okay, or let's put it the other way. So what you know is a scale divergence of the actual distribution. Okay, so, and you don't know C, and again, for some reasons, computational reasons, you are not interested in computing it. So if this is true for every j, so the missing thing is just a normalization constant, not a problem, because mu I over mu j is equal to mu I bar over mu j bar, because basically there is just an unknown constant. So the nice thing again about the design of this algorithm is that it makes use of ratios, and because it makes use of ratios, you do not really need to have a proper PMF. So if the PMF is known up to a normalizing constant, it's okay. You can basically work with this algorithm, and it will work very fine. Again, because you don't really need the absolute values of the probabilities. You just need to have ratios, and so an unknown constancy will not impact your algorithm at all. And that's a big advantage again, like because in some applications, getting this constant will be like computationally intensive or something, and you don't want to do it. But the algorithm can actually work without the need to know what is the C. Okay, so let's move to the next topic, which is queuing. Again, like if you talk about discrete time Markov chains, continuous time Markov chains, then the natural application is basically queuing theory. And a queue is a system in which basically you have arrivals. Okay, so you have arrivals, and those are customers, and they need to be served. And so basically there are servers, but typically there are not too many of them, and so the customers may need to wait in a queue. To be served, and then after waiting some time, they will be served. Okay, and then they leave the system. Okay, so a queuing system is a system, as you see in the figure, is a system in which you have like arrivals from a population, and then here is what is drawn is one server. You can have one server or a number of servers, and again there are like basically sort of waiting places. Again, because typically the arrivals will at times be greater than the number of servers, and so some customers will have to wait. And then there will be a service that is provided to those customers, and once a customer is done, he or she will basically or it will depart from the system. So there is a departure process. Okay, and queues can, again, can be connected to one another. Queuing systems can be like, you can have a cascade of queuing systems. You can have queuing systems basically operating in parallel. The queuing discipline itself can be sophisticated. So suppose that a customer starts the service. The question is, is it guaranteed that basically the customer, will finish the service without any interruption? You can have a queuing system in which this is the assumption, and this is what is done in practice. So once once a customer is being served, that's it. But you can have a queuing system in which there are interruptions. Okay, in which basically the service can be interrupted, and then it can restart again from the point of interruption, or perhaps restart from the very beginning, depending on the situation. So you can have every customer being treated on the same footing, or basically there may be like high priority customers. Okay, and so to be fair, I mean, typically queues will have like a first in, first out. Okay, so if you arrive first, if a customer arrives first, then the customer is served first before some other customer. So FIFO, first in, first out. But again, like you can have a high priority customer. So basically, you can think of an emergency room in a hospital, and you go there because you have like an extreme pain. But basically, despite the fact that you're having an extreme pain, someone may be in a much more critical situation. So he may come after you, but basically perhaps he's like shot, or he fell from a high place, or whatever. Okay, so again, systems may have like sort of this, you don't really stick to the first FIFO, first in, first out, because sometimes actually it does not make sense. Again, it depends on the situation. So my point is that this table on the right is that to tell you that basically the systems can be anything. So queuing systems can be anything. what I said, customers can be anything and the service can be anything. So the queuing system can be, the example that I gave is like an emergency room in a hospital. So basically a hospital, a clinic, an emergency room, basically those can be considered as queuing systems, and the customers will be the patients, and the servers will be the nurses, the physicians, the medical team. The system can be a bus stop, and the customers can be the passengers, and the servers will be the buses. The system can be an airport, and the customers can be the airplanes, and the servers may be the runways. The system can be data network, and basically the customers can be the data, the data packets that are transmitted by the users, and basically the servers can be things like in the network, like routers, like transmitters, receivers, switches, and so on. Supermarket, basically the customers will be shoppers, and the servers will be those checkout stations, and so on and so forth. Okay, so you can come up with so here are basically a list of things that can be thought of, that can be modeled as a queuing system. Okay, so it is something that is very practical, by the way. So it is queuing systems are everywhere if you think about them. Okay, and so again, like the main features are basically arrivals from some population, and this population does not need to be a human population. It can be again like bits in a network, and so there are arrivals, and then they request a service, and sometimes they have to wait, and then they are served, and then they depart. Now, if you want to understand this system, I mean, what are the typical things that you are interested in knowing? One thing will be the delay, like that the overall delay that the customer is expected to remain in the system. So this time can be split into like two times: the time in actual service, but also you have the waiting time, the time that the customer has to wait till the customer gets the service. Okay, so you can talk about delays. You can talk about basically the average number of customers in the queue. You can talk about basically suppose that your queue or your buffer is finite, right? So there was a homework problem in which we have a data network, and then we have a finite buffer. So if the buffer gets more data than it can hold, basically some packets will be discarded. So if the buffer capacity or if the capacity of the queue is finite, and if the arrivals overwhelm the queue, basically there will be lost or dropped packets. Okay, so what is the probability that a packet will be dropped? Okay, so all these are questions that can be answered, using queuing theory, which of course relies heavily on, basically discrete time Markov chains, continuous time Markov chains, renewal processes. Okay, so all these are like sort of the mathematical background that you need so that you can do queuing theory. Okay, so if you read in queuing theory again, like you find that many things we already know. Right? We will see this in the in this lecture, that there are many models and so on that we can recognize immediately because we have already encountered them. Okay, but again, like there are also issues here. Again, especially when you combine queuing systems, having them in series, having them in parallel, having them in a network form, and so on and so forth. Okay, so let's basically start by something that is very famous in queuing systems, which is the candle notation. Okay, so here I will just highlight the surface discipline. That typically it is first in, first out, FIFO. Sometimes it is called FCFS, first come, first served. Okay, but again, this may not be the queuing discipline, but it is sort of the default. So if you do not find, like in a paper, anyone like mentioning anything about the queuing discipline, then the default is that it is FIFO. And and if nobody is talking about finite buffers, then basically the buffer is assumed to have an infinite capacity. Of course, it's not realistic. There are no infinite buffers in reality, but I mean it can be a reasonable assumption in many situations, and it can be unreasonable in many other situations. Okay. So let me focus on the notation, which is sometimes when you describe a queuing system, you write down like a list of letters that may look weird, but I mean basically, if you think about the components of a queuing system, then the first thing, like there are arrivals coming from a population, and so there is an arrival process, and you need to characterize basically the PDF of inter-arrival times. Okay, so the first letter that you write is the probability distribution function for inter-arrival time. Okay, and so if you write down M, if you start with an M, so this M is basically telling that the distribution that you are using for inter-arrival times is exponential. Which means that you are talking about the Poisson process. Okay, and M, you don't say E, you say M, and for memoryless. Okay, so we denote the exponential distribution in this context as M. So if I write M again, it means that we have memoryless. We are using a memoryless distribution for the inter-arrival times, which is the exponential distribution for for basically if we talk about the family of PDFs. Now, when a customer is in the system, basically the surface time, again, the surface time is typically modeled as a random variable, so it will vary from customer to customer, and it will follow a certain distribution. Okay, so we have another letter. So the second letter is a letter that tells you information about basically the surface duration. So if you write another M, another memory, so here we are talking about basically the surface times being exponentially distributed. Okay, but you can have something else. You can have like MD. So MD here, D is deterministic, which means like sort of fixed. So here the random variable describing the time of surface is a degenerate random variable. So suppose that perhaps in a network or something, basically the time needed to serve a packet or something like this is just fixed. And so this can be, so basically degenerate random variables are allowed to be used here. So you can be like in this case of basically the surface time being deterministic. Okay, and you can use deterministic for the arrival. No one is preventing you from doing this. My point here is that the first letter, again, like when you have a queuing system, it is described by sequence of letters. The first guy will be a distribution. You find M for exponential, D for deterministic, EK for Erlang with parameter K. So basically Erlang K is the sum of KIID exponentials. G general. I mean, sometimes you are so ambitious and you want just to basically analyze your system with a general inter-arrival time. The surface time again can be one of those guys. Then the third thing that you mention is basically the number of servers. Okay, so MM1, it means that so if you read something like this, that the inter-arrival times are exponential, the surface times are exponential, and there is just one server. Okay, there is just one server, and and then again you can have just those three guys, or you can have another three. So the other three will tell you that the fourth guy will be the maximum capacity of the system. So this will be the size of your buffer. Okay, so buffer size. Okay, so this is the buffer size, and if it's omitted, so if you write just the three letters, it is assumed that you are talking about a buffer size that is infinite. So you are talking about an infinite queue. So if you don't write it, the default is that it's infinite. Now you have the fifth thing that you may basically add to your notation to describe your queue is the total population. Again, if it's omitted, then it is infinite. And the last thing is basically the queuing discipline or the surface discipline. And if it's not mentioned, then first in, first out, or first come, first served. Okay. Like let's basically do here the most straightforward queuing system. Note that remember the advantages of using exponential distributions. Exponential distributions are memoryless, and so if you have arrivals following a Poisson random process, and if the surface times are exponential, then for example you can model your queue using something like a continuous time Markov chain. Okay, so basically MM is like the first order of business, really. Once you start doing things other than the exponential, for example, the whole framework of continuous time Markov chains will not be applicable, right? Because you need your sojourn times to be exponential. Okay. So that's the easiest queue. So it's MM1 again. As I said, this is the notation that is used. First M for memoryless, it means that the inter-arrival time. So this first M means that arrivals follow a Poisson process, a Poisson random process, and so this means that the inter-arrival times are exponential, and the second M means that the surface times are exponential, and this one here means that you have one server. We just have one server, so all the customers are competing basically on just one server. But here again, like we omitted the other three letter or three pieces of information that we may include, and so once we do this omission, it is understood that we are using the defaults. So the defaults are that we have an infinite buffer, we have an infinite population, and that the queuing discipline is first in, first out. Okay, so I will just jump to this. Suppose that the arrival process is a Poisson process with parameter lambda. So it means that the inter-arrival times are exponential lambda. And so basically, the rate of transition. So this system here is, it can be modeled as a continuous time Markov chain. Specifically, it is a birth-death model. And the arrival rate, so to go from state I to state I plus 1, basically the rate of transition is lambda, okay, and the rate of transition from I to I minus 1. So this will be what? I mean, this will be the surface. I mean, so you go to the lower state if basically one user is done, okay, and so. So the rate here is mu, which is the parameter characterizing the surface time. Okay, so the surface time here is exponential with parameter mu. Okay, and then there are self transitions, of course, that are typically omitted to reduce clutter in the figure, in which, like, those will be the diagonal elements here in the Q matrix. So starting from the second row, you will get those minus lambda plus mu. So so basically the sojourn, each state it has this. Okay, so the sojourn time of each state is exponential lambda, because think about it. If you are in a certain state, what are the possibilities? So you are basically things depend on what? Things depend on the minimum of the surface time and the inter-arrival time, right? So suppose that you have at some time instant, basically the system is in state 2. So there are two customers. Right? So now what are what are the possibilities for the future of the system? Well, so basically, once you say that the system, it has two then what can happen is that you get a new arrival. Okay, so you can get a new arrival, and the time to get this new arrival is exponential lambda. Or maybe actually the server will finish serving. The server will finish serving the customer who's basically being served, and in that case, this time is exponential mu. So you will get out, so basically the time that you remain in the state 2 or any other state I, that is where I is greater than 0, is basically the minimum of these two random variables. Okay, so the arrival process is assumed to be independent of the surface process, and so basically the sojourn time of any state is the minimum of exponential lambda and exponential mu random variables, and so it is an exponential random variable with parameter lambda plus mu. Okay, and then you do a transition. Will you do the transition to the upper state or to the lower state? It depends on which of the random variables is the minimum. So if it's the inter-arrival time, then you will go a transition. You do a transition. You have one more customer in the system. Okay, so the states here are basically we are tracking the number of customers, or you basically if the minimum of the if the minimum of the surface and inter-arrival times is the surface time, then one customer is done, and basically the state of the system will be reduced by 1. So again. Because all distributions, all relevant distributions here are exponential, we are capable of modeling the system using a continuous time Markov chain, and we can easily write down the state transition, the state, the rate matrix, the transition rate matrix. And basically we can play with it and like do things like what is the stationary distribution. Okay, and if you have a continuous time Markov chain and you have access to the Q matrix, to the transition rate matrix, then basically you can obtain the stationary distribution by solving the equation. You get a row vector of the stationary probabilities. You multiply by Q, and it should be equal to the all 0 row vector. And so you start writing down your equations as we know, and then you solve them. Okay, so basically here you do a few iterations and you get a pattern, like so by 1 is equal to lambda over mu by 0, and then by 2 is lambda over mu squared by 0, and so on. So we see that there is a pattern like that by k is equal to lambda over mu to the k by 0. Okay, so this is basically when you do the analysis of using this Q matrix. And yeah, I mean, so this will be, what you do is that you get like by n is here row n, I write row n by 0, and this row is lambda over mu, and then you say, so okay, great, every probability now is expressed in terms of by 0, so let's get by 0, and we get by 0 using the normalization condition that basically the sum n from 0 to infinity of by n should be equal to 1. And so this tells you that by 0 and then summation n from 0 to infinity rho to the n should be equal to 1. So basically you are able to find the solution, if rho is strictly less than 1. So if rho is 1 or rho is greater than 1, actually this summation will not make sense. So you can see here that basically you get a stationary distribution, but it is conditional. Okay, it is a conditional statement. You are not guaranteed to get a stationary distribution. You get a stationary distribution so long as the parameter rho, which is lambda, the parameter of the inter-arrival time, and mu over mu, which is the parameter of surface time, this ratio should be strictly less than 1, so that this geometric series converges, and so we have it will be 1 over 1 minus rho, and this is equal to 1. So by 0 in this case, under this condition, by 0 is equal to 1 minus rho. And so you insert it here, okay? And this will be an expression. For by n for every n. So if n is 0, it is 1 minus rho. If n is 1, the stationary probability by 1 is rho 1 minus rho. If it's by 2 is rho squared 1 minus rho, and so forth. Okay, so you can know those guys, and then you can start asking questions like, what is the average number of customers in the system? What is the average number of customers? Okay, again, it's one of the interesting questions. And what you can do is basically say, okay, I mean, so I have a distribution. Telling me, what is the probability of having n customers in the system, and so you can just multiply by n, and then sum, so that you get the average number in the system, and you will get here the geometric series, but multiplied by n. And again, like, you can do this sum in a number of ways. One of them is just to use software, but it's actually doable by hand. But we don't have time for it. This summation can be evaluated to give rho over 1 minus rho. So this is the average number of customers in the system. Now you may be interested in the average people who. So basically, the people in the system are so if the state of the system is 5, so there are 5 customers. We have one server in our model, and so basically one of the 5 is being served and the others are waiting. Perhaps you are interested in in the average number of like waiting. Okay, so here, rather than multiplying by n, here you multiply by n minus 1, because among the n guys in the system there are basically one in surface, and the others are waiting. Perhaps you are just interested in those who are waiting. Okay, and the mean number of in surface will be basically the difference, the difference between these two quantities, and in our case here it will be rho, which is 1 minus by z. Okay, so any questions so far? Okay, so the probabilities, the bias that we obtained, in a general case, will not tell you what is going on from the point of view, from the perspective of an arriving customer, generally speaking. Okay, so what do I mean by this? Okay, so let's talk about an example before we dive into this pasta property. So suppose that rather than having MM1 is our is basically what we are doing right now. But suppose that you have a deterministic inter-arrival time, which means that you have a customer arriving every t seconds. Every t seconds you get one, and it's exactly in math. So to be exactly every t seconds a customer will arrive. Okay, so suppose that the surface time of a customer is basically is some distribution. Perhaps it is not deterministic, but it is a distribution that is less than t, almost surely. So with probability 1, an arriving customer will be served, and the time of surface with probability 1 is strictly less than t. Okay. So from the point of view of an arrival, no arrival will see a busy system, right? Every arrival will see an empty queue. Again, so this is the time axis. So here we have an arrival, okay, of, let's say, C1. So this is first customer. Now, according to our model, this customer will be served, okay, and the assumption is that if the server is idle and a customer arrives, basically the server immediately starts providing the surface. Okay, so here's an arrival, there will be a surface time, okay, and then C1 leaves the system after surface. And this time here, so this is the surface time, is assumed to be as time is assumed to be less than t. Okay, so it can be anything, you know, but it's less than t. It's okay. It does not need to be like deterministic. It can be like a proper random variable, but it should be, you know, less than t almost surely. Now the next, you know, after t seconds, okay, some, you know, so this is, you know, basically this is t. After t, then here is arrival of C2. So that's the second customer. Well, the second customer will see that, you know, the system is empty because basically the arrivals happen every t seconds, while basically the surface is completely, is completed in less than t seconds with probability 1. And so from the point of view of an arrival, the system is always empty. You know, so if you are one of those arrivals that arrive every t seconds, you will never arrive and find that the server is busy. Okay. But basically, for someone investigating the whole time axis, is it true? You know, is it true that basically the server is, you know, is idle at all time? Of course not. Basically, there is a fraction of time in which this, you know, the server is idle. So basically, this will be you know, t minus the mean service time over big T. Okay, so so again, from the point of view of an arrival, it's always the case that the buffer is empty. But if you talk about, you know, what is the probability? If you ask what is the probability that the buffer is idle, the probability that the buffer is idle will be, you know, the time, you know, it's t minus, you know, the surface time, and if you want the average of this thing, so it's t minus the mean surface time divided by t. So this will be by 0. The moral of the story is that once you start, you know, using things other than memories and so on, you need to make a distinction between, you know, those pi probabilities that you obtain and what actually, how actually the queue is experienced by the arrivals. So you may think that these two things are the same, but they are not the same. From the perspective of the arrivals, they may see statistics different from basically like someone you know, who's not an arrival, who is basically studying the system at any possible time instant. Okay, so again, like if you look at any time, you know, you are not bound by the arrival process. So suppose that you are some sort of an inspector. So an inspector, you can arrive at any time whatsoever. If you arrive at let's go back to our example. If you are an inspector who arrive at any time whatsoever, again, there will be times in which you see that the buffer is busy, and there will be times in which you see that the buffer is idle. But if you are part of the arrival process, which here is very strict, and, you know, we have just an arrival every t seconds, then you will never see actually the server being busy. You will always find the server idle and the queue empty, and, you know, once you arrive, you will receive your surface, and it will take less than t, and then you depart, and then there will be a new arrival, and so on and so forth. Okay, so this is a motivation to, you know, understand something that is called the Basta property. You know, because like Basta property, like for you know, for when, like if you read like for the first time, you may think that it is sort of like very obvious, you know, but it is not. You know, so the Basta property telling you that if you have the probability that Poisson arrivals, okay, so here the using the exponential distribution is crucial. So the probability that Poisson arrivals will see NA customers in the system upon arrival is equal to the fraction of time that the system spends in state NA. Okay, again, you may think that, you know, oh, okay, I mean, this should always happen. No, it is not. This may seem like an extreme example, but it tells you that, you know, things are complicated. And sometimes you need to study distributions from the point of view of the arrival process itself. Okay, rather than again allowing this sort of some inspector or someone who can basically arrive at any time. Okay, so the statistics from these 2 points of views may be different, and this may be crucial in like analyzing and understanding your system. Here is the good thing for the MM1 queue. Basically, the arrivals will see the probability that you see you see J customers in the system is this by J. So the by J that we get using our tricks here, you get the stationary distribution of the Q matrix. It is basically what you need from the perspective of the arrival. But again, this is very specific. Okay, and this thing, of course, it has a proof. I didn't include the proof here. Okay, but it is something that is in case you use queues in your work later, you need to keep this in mind. And what is the difference between like using a memoryless distribution and using some general distribution? Okay. Now let's go back to MM1 again. From the point of view of MM1, again the question is is the probability that an arriving customer sees J customers in the queue equal to by J? Yes, in MM1. Yes, if you have this pasta property, Poisson arrival C time averages. Generally, no. Okay, so this is very important. And if you want like to compute things from the perspective of the arrivals, you will have like to obtain what probabilities by what probabilities they basically perceive the system. Okay, the way but here basically the probabilities are the buys. Okay, any questions so far? So the waiting time in the system, you come and then you wait. Well, I mean, so what is the distribution of the overall waiting time? Well, if a customer arrives and there are n customers already in the system, then because the queuing discipline or the surface discipline is first in, first out, or first come, first served. So if you come and there are n customers already there, it must be the case that basically those n customers must be served, and then you will spend basically some time being served yourself. Okay, and so the amount of time that is spent in the queue will be the sum of n plus 1 IID exponential mu random variables, right? Because every surface time is exponential mu. We will assume that basically the surface times are independent from customer to another. You may debate that assumption and say that you can think of examples in which basically the server serving some customer will somehow according to how things go, it will impact what the server is doing with the next customers. Okay, but ignore this. Let's assume that basically the surface time is independent from customer to customer. So you have basically a total of n plus 1 service times to wait. The surface times of the n guys in the queue who have arrived before you, and then there is your own surface time. Okay, and so the surface time, it has a distribution. So the conditional distribution, given that there are n customers already there in the queue, So what I'm talking about now is not the unconditional distribution. Given that there are n guys in the queue, the conditional distribution will be the sum of n plus 1 IID exponential mu, and it has this PDF. Now, if you want to have the so this is conditioned on having n customers already there. If you want the unconditional PDF, what you need to do is to take this conditional PDF and then multiply it by the probability that there are n customers, which is by n in our case. Again, because of this pasta property, this nice property that from the point of view of a new arrival, basically what is the probability of encountering j customers already in the queue? It is pi j. So here you take basically this PDF, which is conditional. You multiply by pi n, which has a formula, we obtained it, and then you do a summation. Okay, so you average, and if you do so, you will find that the mean, so you'll find that the waiting time in the system, it has it is exponential. So the unconditional waiting time, again, so you condition on n, say, okay, perhaps I will arrive and no customers are there. Perhaps I will arrive and there is some guy there, 2 guys, 3 guys, and so for each one, again, if there are n, you will have to wait n plus 1 IID exponential mu, and then you can basically, so you obtain first the conditional waiting time given n, and then you multiply each conditional PDF by pi n, and then you sum, and you will get this nice result that the waiting time, it's like the overall delay that you will encounter in the system is exponential. And it has a parameter which is mu minus lambda. Mu minus lambda. Remember that actually for our system, to have a stationary distribution, to be stable, as they say, you must have lambda less than mu. Okay, so don't worry here about having mu. So this is actually the case of interest. If mu is less than lambda, then basically the number of people in the queue will grow without bound. Okay, and so basically the number of customers will tend to infinity as t goes to infinity. Okay, so we will say that the queue is unstable. Okay, but it's not the case of interest. Here we have the case of interest is when mu is greater than lambda, or basically the parameter of the arrival process is less than mu, the parameter of the surface process. So this is exponential, and so basically, what is the average waiting time in the system? So again, if this is the parameter of the exponential, then the average waiting time is 1 over mu minus lambda. Okay, it's 1 over mu minus lambda, and this will be the time that you have to wait in the system. Note that if lambda approaches mu from below, so if the arrival rate gets closer and closer to mu, then basically this thing will explode. Okay, so you will encounter, you will have to go through, longer and longer waiting times. So we computed 2 things. So the average number in the system, in the queuing system, and that was rho over 1 minus rho. So that's small l. Now the average waiting time is 1 over mu minus lambda. So you can take this mu as a common factor, and then lambda over mu is rho, and so it is given by this. Note the following, that the average number in the queue is, if you take its ratio over the average waiting time. So one of them is, rho over 1 minus rho. One of them is rho over 1 minus rho, and the other is 1 over mu multiplied by 1 minus rho. Okay, let's actually do it. So rho over 1 minus rho, and the other one is 1 over mu 1 minus rho. So 1 minus rho will go with 1 minus rho, and then rho itself is defined as lambda over mu, and this mu will come upstairs, and so the ratio is lambda. And so the average number in the queue is the average waiting time multiplied by the arrival rate, which is lambda. Okay. And this is for our our MM1 system, sort of the most straightforward queue. Exponential inter-arrival times, exponential surface times, just one server, and so forth. Now, it turns out that in queuing theory, that this relationship is true in much more sophisticated settings. And so this is one of the fundamental results in queuing theory called Little's theorem. So Little's theorem or Little's law or whatever you want to call it is basically this idea that even in a queuing system in which we don't really impose exponential inter-arrival times or basically exponential surface times, the average number of customers in the system, the average number in the queue, is related to the average waiting time or the average delay in the queue. And they are related in a very particular manner. L is equal to lambda W. Okay. So, this is interesting. And again, like this is no, it is a strict equality. It is a strict equality. So this is the thing that of course in our case here it is a strict equality because we did the derivation and so on. The thing that we skipped here is the basta property. So there was a step in which okay, so let's cancel it. So there was a step in which again you need to find the PDF. So this is like the hard way of doing things, in which you do it, you actually obtain the PDF of the waiting time. So here you will need to ask yourself this question from the point of view of an arrival: what is the probability of encountering n customers already there in the system? Is it really by n? Are we justified? So that's the basta property, and it's not true in other, once you start using general arrival processes, perhaps a renewal process with an inter-arrival time that is not exponential. Okay, but here the derivation is exact. Again, the missing thing is the derivation of the basta property itself, and we reached this formula. So this formula is also exact. It's not an approximation. It's not a cool approximation that sort of works in practice, but it is not actually a mathematical equality. It is a mathematical equality, and so we will spend some time with this very nice result. And I want to give a derivation that's sort of general. So the claim is that this tiny result, that L is equal to lambda W, it's available even in sophisticated queuing systems. So the derivation here will be sort of different. Because again, we want to be as general as possible. So the motivation was that people started studying different types of queues like MM1 and some of its generalizations, and they discovered that every time they compute small l, the average number, and the average delay or average waiting time in the system, they get this relationship that L over W is equal to lambda. And so what is going on here? Okay, consider a queuing system. Now, Cn denotes the nth customer. Okay. Now, Cn arrives and enters into the system at time Tn. Okay, so now we will basically sort of give numbers to our customers, C1, C2, C3, and so on. So the nth customer will arrive and enter into the system at time Tn. And those are ordered. Those are ordered in the sense that, the second customer arrives after. So basically, you rank them based on, whoever arrives first. Okay. And the arrivals are a counting process, something like, Poisson process, renewal process, so n of t is the maximum n such that the arrival happens, Tn is less than or equal to t. Arrival happens before or at t. Okay. Now, what will happen to customer Cn in the system? The customer will spend a time in the system. This time is basically two components. So there is a waiting time, doing nothing, just waiting for one of the servers. If you have more than one server to be idle, so the customer Cn will spend Wn units of time inside the system. The other component is once a server is available, the customer can be served. So the overall time in the system is basically Wn here, units of time, and the customer will depart at Tn plus Wn. So basically the nth customer will arrive at time Tn, and the nth customer will spend Wn in the system, and basically Tn plus Wn, this is Tn with the superscript d departure. That's it. The departure times are not necessarily ordered, because again, like we are talking about a system in which, like, you may have perhaps two servers, and so maybe customer 1 will come and will enter service, customer 2 will come after customer 1, but perhaps customer 2 will finish the service before customer 1. So the arrivals are ordered, the departures are not necessarily ordered. Okay, of course, if there is just one server, then customer 2 will have to wait for customer 1 and so on. But again, like, I am trying to give you, a derivation that is so general, because Little's law or Little's theorem is a very general, amazingly general, basically property of queues. We'll assume, that Wn is finite almost surely. Okay, so, you may like push things to extremes. And you can say, for example, that one customer with a non-zero probability may remain an infinite time in the queue. Okay, so you can play these games, but I mean, let's get a bit realistic, and so we will assume that the time spent by the nth customer in the queue, regardless of n, is finite almost sure. It can be huge, but it is finite. Typically, if Wn goes to infinity, we have a problem in the system itself, and we will not be interested in. Typically, this system will have a growing number of people, and the delay will grow to infinity and so on. So those are sort of unstable systems that are not of interest to us. You can count, of course, the departure. You can have a counting process for departures. So in queuing systems, you can have like two counting processes. Okay, so so it's a more sophisticated version of a count. It's not just one counting process, because you can keep track. You can keep track of the arrivals, and then you can keep track also of the departures. Okay, so there is a counting process for the departures, and it's always true that the number of so at time t, the number of departures that happened from 0 to t are less than or equal to the number of arrivals, right? Because I mean, you cannot have more departures than the number of arrivals from 0 to t. Okay. Now you ask yourself this question. We want to write down a formula for the number of people, the number of customers in the system, in the queuing system at time t. So basically, let's talk about the nth customer. When is the nth customer in the system? Okay, so here is the nth customer will arrive at Tn. The nth customer will basically depart at Tn plus Wn, which is Tn superscript d. So basically, for customer n to be counted, when you basically count the customers at time t, it must be the case that t is somewhere between Tn and Tn plus Wn. Okay, so basically customer Cn is in the system at time t if and only if t is between Tn and Tnd. And so if you want to track the number of customers in the system at a particular time instant t, then what you can do is that you have an indicator that tells you basically it is 1 if t is between Tn and Tnd, and 0 otherwise, and then you basically sum over all n. Okay, so this will give you basically the number of customers at time t. So those are the customers for which this inequality is true, for which t is between the arrival instant and the departure instant. The time of departure is the time of arrival plus the time spent in the system waiting and then being served. Okay, so we have, then we have two inequalities here, that t should be greater than or equal to Tn, right? It must be the case that the arrival time to count the customer, first order of business is, to count a customer, it must be that the time instant t in which we study the system must be after the arrival time of the nth customer, so that we consider the nth customer. So Tn is less than or equal to t. But also you need another inequality, which is that the departure happens after t. So I will write down things in this form here that, again, it's another way of writing down L of t, that you can write it that, rather than having your index as the natural numbers, the index n will be the subset of natural numbers such that Tn is less than or equal to t. So this will be the first inequality. And then the indicator will take care of the other inequality, telling that t must be less than the departure time of the nth customer. And if you count up to n such that Tn is less than or equal to t, you can, rather than again having a summation over the natural numbers, you can count n from 1 to n of t, and you can write down this inequality, t less than Tn plus Wn, as a summation n from 1 to n of t, and then you can write down things as an indicator with the surface time exceeding the time difference between t, the instant at which you examine the system, and the arrival time Tn. Okay, so we will assume that those guys exist. Okay, so lambda is the limit as t goes to infinity n of t over t. And this is a quantity we are familiar with from our study of renewal processes. This will be called the arrival rate into the system. Small w will be the average time spent by customer in the queue. And so what I will do here, I will sum every time spent by customer in the system. So I will sum them and then divide by n, and then we will take the limit as n goes to infinity. So by definition, this will be w. And then we have the average number of people in the system, and so this will be L of S, L of t, and then integrated from 0 to t. So L of t integrated from 0 to t, and then basically we divide it by t, and take the limit as t goes to infinity. So the theorem, so Little's theorem, this is like the formal way of saying Little's theorem, is that if both lambda and w exist and are finite, so if it happens that actually this limit exists and gives you a finite positive number, and this limit exists and gives you a finite positive number, in that case we have our magic formula that small l defined as such will be equal to lambda multiplied by w. Okay. So if you look to the definitions, basically the average number of customers in the system is defined to be the limit as t goes to infinity 1 over t, the integral of L of t. So I just to have the integration from 0 to t, I will change here. I will use a dummy variable of integration s ds. So this is the quantity, and I want to show that basically this is lambda w, and like, if you try to do this like directly, it's not feasible. At least our ancestors tried to do this, but it didn't work, and so you need a trick to compute the limit. How can you show that this limit actually is, so basically this is desired, is to show that this is equal to lambda w. So the idea is sandwich theorem. Okay, so nothing else. So we will use the sandwich theorem, which means that we will take this, this quantity, specifically the integral, and we will upper bound it, and we will lower bound it, and then we will show that if you take the upper bound and the lower bound, divide them by t, take the limit as t goes to infinity, you will converge to lambda w. Okay, so I mean, some people know this as the squeeze theorem. Okay, regardless of how you, of what mean you give to it. Again, the idea is we will go for bounds, upper bound, lower bound, and then show that both bounds will converge to the some exact same limit. So it means that the quantity that is living between these two bounds, it must be converging to the exact same limit. Okay, so so this is L from the previous slide. It's a summation, including, so you basically L of S, the number of customers at time S. So it's summation over the natural numbers, and we have basically the customer N will be there in the system at time instant S if S is between the instant of arrival of customer N and the instant of departure. Okay, so we will basically write down this summation, and again, as I said, once you have an inequality, something less than or equal to something less than something less than something, it is actually two inequalities, and let's separate them into an indicator of an inequality S greater than or equal to Tn, and another one S is less than Tn plus Wn. Okay, then we have an integral from 0 to t, and then we have a summation, and what we will do is that we will interchange the order. Well, we are dealing with quantities here that are 0 or 1, and so we can interchange the order, and we will bring the integral inside. Till now we have equalities. Okay, now if you bring this integral inside, and your dummy variable of integration is S, S must be greater than or equal to Tn. S must be greater than or equal to Tn. So basically, we will change. We will basically eliminate this indicator, but we will make the lower limit of integration equal to Tn, because again there is an indicator. Again, it comes from this. This must be satisfied. So now our integral, rather than starting from 0, it should start from Tn, and then this indicator is basically incorporated in the lower limit of integration. What about the upper limit of integration? Well, the original integration is, it comes with a t, but then we have this inequality in which the variable of integration is upper bounded by Tnd, which is the time of arrival, the time of arrival of customer N, plus the time spent by customer N in the system, and so S is also upper bounded by this thing, and so S, your integral, should go up to the minimum of these two guys. Okay, it should go up to the minimum of these two guys. Okay, and to note something, that S should be greater than Tn. If it happens that T is, which is the upper limit of integration, is less than Tn, then this integral is 0, right? So if this lower limit on S, lower bound on S, exceeds T, that's it. I mean, you basically your integration is 0, and so you need this indicator here. Okay, this indicator to make sure that basically your upper bound is greater than your lower bound. Okay, so again, what we are doing is that we have L of t, which is a summation over the natural numbers indicator that to be counted among those customers that are present in the system at time t, it must be the case, that Tn is less than or equal to T less than, Tn plus Wn, and this is basically Tnd, the departure time of the nth customer. Now, by definition, we define L to be limit as t goes to infinity 1 over t integral 0 to t and then L of s ds. Okay, and so what we are doing is that this limit is sort of impossible to be done directly. So what we will do is that we will take this quantity, or specifically the integral, and we will upper bound and lower bound it. So now we are studying this. We are studying this integral, and till now we don't have actually any bounds. We are just careful in making sure that everything makes sense. Like the integral is from 0 to t, so basically this s, so s has another inequality, which is, or actually, yeah, okay, no, it's unequal, but it's to be understood as basically a pair. So s and t. Okay, and so you need to to write down things carefully. So for example, t must be greater, so s is greater than or equal to tn. Well, if t is less than tn, then your integral is 0. So you have this indicator here, and then you can just have an integral with respect to s that is free from all indicators, and it is a very doable integral. It is just the difference between the upper and lower limits of integration, which is this quantity. Okay, so let me, this is, don't forget, this is integral 0 to t, L of s ds. Okay, no bounds till now, but now this is the time for our upper bound. Okay, so the minimum of two quantities is less than or equal to each. So you can upper bound this minimum by t. You can upper bound this minimum by Tn by Wn, and in both cases you are correct. So if we upper bound this minimum by Tn plus Wn, then the nice thing is that basically the upper bound Tn will cancel this minus Tn, and then you are left with Wn. Okay, so again, the upper bounding trick here is to take this minimum and upper bound it by Tn plus Wn, which will lead to this upper bound. Okay, and so it is Wn, and then there is an indicator for every Tn is less than or equal to t. So we can basically rewrite this summation as a summation n from 1 to n of t. Remember that n of t is the minimum n such that Tn is less than or equal to t, right? Maximum, sorry, the maximum n such that Tn is less than or equal to t. And so basically this summation with an indicator that Tn is less than or equal to t, rather than going from 1 to infinity, you can just say, okay, I will incorporate this indicator in here. Okay, I say, okay, I will sum n from 1, 2, 3 up to the n that satisfies that Tn is less than or equal to t. Well, by definition, this maximum n will be big N of t, which is the counting process of the arrivals. And so this is the upper bound. It's this summation here. Okay, any questions? I think I mean, oh yeah. The lower bound. Okay, so the lower bound is that, so go back here. So this is the step in which we applied our upper bound, and again, the upper bound here is not like something fanciful or anything. It's just you have a minimum of 2 terms, and you said, okay, I will just take this as my upper bound on the minimum, and so it's upper bound on the overall quantity. Now for lower bound, you come here, and here is how you will do the lower bound. So here, basically, we have an indicator that t is greater than or equal to Tn. So here you have an indicator that Tn is less than or equal to T. So you include in your summation any arrival instance that satisfy that they are less than or equal to T. So what you will do is that you will have Tn less than or equal to T minus Wn. T minus Wn. So you go below T, which means that you eliminate some terms in this summation, and we are summing in a negative quantity. Okay, so the trick here again is to have this upper bound that indicator T greater than or equal to Tn is greater than or equal to T greater than or equal to Tn plus Wn. Okay, so here again, like as a function, as a function of time, what is this indicator here? So there is an instant Tn here, an instant Tn plus Wn. So indicator T greater than or equal to Tn is a function that looks like this. So it is 1 once T is above Tn, and then it's 0 here, while the other function in which T is greater than Tn, the other function it's 0 like this, and then it is 1. So the green function is basically the green function is greater than or equal to the blue function, which means that the blue function is a lower bound. So this is exactly what is done here. So here the trick is a very fine trick. It's basically just insert this plus Wn, and then you have greater than or equal to. Now your indicator is saying that T is greater than or equal to Tn plus Wn. So whenever this indicator is equal to 1, whenever this term is an active term, it must be the case that T is greater than Tn plus Wn. So which of these guys will be the minimum? So the minimum will be Tn plus Wn. Now it is the minimum. Okay, so given that this event is true, this Tn plus Wn will be the minimum, and so again the difference between the minimum and Tn will be Wn, but now our indicator is different. Our indicator here is indicator Tn less than or equal to T. Our indicator here is T greater than or equal to Tn plus Wn, and so this is our lower bound. Okay, so I think perhaps the upper bounding is much easier than the lower bounding. So basically for the upper bound, the idea is that okay. So this is what we have from the previous. This is the upper and lower bounds. Okay, and yeah, the idea is, take the integral, divide by T. So this is the upper bound, and so divided by T, and then we will do things that look familiar. We did things like this when we studied renewal processes. So you have a summation n from 1 to n of T, and then we have factor 1 over T. So divide and multiply by n over T. And so you have basically the product. The upper bound can be written as the product of two quantities. One of them by assumption, we assume that there is this positive parameter lambda, and lambda by definition is basically this limit as t goes to infinity of n of t over t. So this is our first guy here, by assumption. And what about the second guy? Well, by assumption, we define the average delay in the system, as well as limit, by definition, n goes to infinity, 1 over n summation k from 1 to n w of k. So you sum the surface times, the waiting times, the overall waiting times of the n customers, divide by n, and then take the limit. Okay, so here again, since the arrival process is a counting process that is growing to infinity, okay, and it is here n of t and n of t, then as we define this thing will converge to w. Also, if you replace small n by big N of t, it will also converge to w by assumption, and by the fact that n of t, like what we did in renewal processes, n of t converges to infinity almost surely. So the right-hand side, after taking this and dividing by t and taking the limit, the right-hand side, the upper bound converges to the desired product lambda times w. Okay, so to finish this thing off, we need to go to the lower bound and show that it converges to LW, or it converges to a limit that is above, greater than or equal to lambda W.